Hello, everyone. This is Taimur Abbas, your host for YP webinar series sponsored by IEEE Vehicular Technology Society. We have a newly started IEEE VTS Ambassadors Program, and under the Ambassadors Program, our ambassadors are invited to give talks on the topic of their interest. And today we have Dr. Ji Gao from Carleton University in Canada. He's one of our newly appointed IEEE VTS Young Ambassadors. And any of you who are listening here, and if you are interested to know more about the YP Ambassadors Program, I will be happy to assist, and maybe you can be one of our ambassadors for year 2024. So I would like to hand over the floor to Dr. Ji Gao. Welcome, and thank you so much for taking time to share about the Beyond 5G. The topic is like leveraging AI and digital twin for automated network management. The floor is yours. Thank you.
Thank you, Dr. Abbas, for the introduction and for arranging this webinar. It's my great pleasure to participate in IEEE Vehicular Technology Society Young Professional Activities. I'm Jay Gao. I'm with Carleton University, and I started my faculty career not long ago. The topic I'm presenting today is Beyond 5G, Leveraging AI and Digital Twin for Automated Network Management. This is collaborative research with Professor Shen, Professor Zhuang, Dr. Zhou, Mr. Hu from University of Waterloo, and Professor Zhao and Dr. Li from Toronto Metropolitan University. So I'll first give an introduction, and I will talk about two aspects of our proposed idea for Beyond 5G, holistic network virtualization and pervasive network intelligence. To better illustrate our idea, I will present a case study and then conclude this talk. Well, since we're talking about Beyond 5G, so it's relevant to take a look at 5G and see what happened. The first 5G specification by 3GPP was made available in release 15. And in that release, 3GPP specified non-standalone, standalone architectures and introduced critical communications, which later became more focused on ultra-reliable, low-latency communication. Release 15 also includes enhancement of machine-type communication, Internet of Things, and vehicle-to-everything communication, and so on. Then in release 16, 3GPP focused on enabling 5G for verticals, various industrial applications. New elements introduced in release 16 includes 5G positioning, network automation in terms of ENA and private network. Release 16 also includes enhancement of slicing, service-based architecture, and so on. Release 17 was made during the pandemic, and the new element in release 17 includes the integration of satellite components in terms of satellite access. And there are also enhancements such as enhancement of positioning, energy efficiency, private network, and so on. Recently, 3GPP made release 18 available, so it was published in December 2023. We don't have a stable version yet. Release 18 is the first 5G advanced or 5.5G specification. And in release 18, 3GPP introduced satellite backhaul, artificial intelligence, machine learning management, extended, augmented, and virtual reality and immersive communications. And release 18 also includes enhancement of non-terrestrial network support, positioning, network slicing, and so on. So 5G has introduced and adopted many new technologies and designs, some of which were covered in the previous slides. They include millimeter wave, massive MIMO, multiple access edge computing, and so on. And it is well known that 5G has three predefined use cases: enhanced mobile broadband, ultra-reliable low-latency communication, and massive machine-type communications. So knowing the basics of 5G, we want to ask a question, what motivates us to look into beyond 5G? And this is really an open-ended question, and different people may have different answers. And today I want to talk from three aspects. The first is coverage. So despite the initial efforts of integrating satellites and non-terrestrial networks, currently 5G still has limited access in rural and remote areas. Second, architecture. So the 5G architecture has limited support for artificial intelligence and programmability. Third, management. So currently 5G has limited automation and adaptivity in network management. So what do we need in beyond 5G? Well, accordingly, three things. First, ubiquitous and seamless coverage. And this means cost-effective satellite network and non-terrestrial network integration. And this integration should extend beyond access and backhaul. For example, layer 3 designs are also important. Second, flexible architecture. So this means we will need a more flexible architecture to facilitate AI and other paradigms. Earlier, we mentioned that 5G has three use cases. It is a consensus that 5.5G and 6G will have more use cases and more diverse use cases. So the flexible architecture is necessary for supporting the new use cases. Third, intelligent network management. So this is necessary to automate network performance optimization and to satisfy service requirements. So before getting into details of our proposed idea, I would like to first talk about emerging applications in beyond 5G. And the first category of emerging applications is immersive communications. On the left-hand side, I have a screenshot from a YouTube video on augmented reality sport. So there are human users, real human users in a physical venue. However, other elements of the gaming, you can see the laser balls and the laser shield are generated in virtual reality. On the right hand, we have a figure from our recent survey paper towards immersive communications in 6G. This illustrates different types of immersive communications, which includes extended reality, haptics, and holography. The second category of emerging applications is networked robotic and autonomous systems. This could include both cooperative operation among service robots and human-machine interaction and collaboration. So such applications are particularly of interest in industrial environments, and they are considered to be a feature of Industry 5.0 or the next industrial revolution. The third category of applications is next generation vehicular applications. On the left-hand side, I have a figure that shows remote driving or teledriving. So by now, we are all familiar with the idea of working from home. However, this is rare for drivers. The idea of teledriving is to project the driving environment to the monitors surrounding a driver so that the driver can also drive remotely. Although I would be hesitant to sit in a car if the driver is not in the same car, but such application can be attractive in certain scenarios, such as freight truck driving. On the right-hand side, we have a figure that shows the full autonomous driving. This would require advanced vehicle-to-everything communications. Now, of course, there are many potential applications for beyond 5G, and it's impossible to go through all of them. Instead, I will try to summarize some trends and paradigm shifts from the applications we have discussed so far. Well, the first one is the reality we're living in is being reshaped, and the boundary between the digital world or the virtual world and the physical world is disappearing. So this means in the near future, it will be important for networks to deliver immersive experiences for users. Second, multimodal communication and multifarious tasks. The future communications will involve synchronized delivery of voice, video, haptics, and so on. And future networks will need to integrate functions such as positioning, sensing, computing, communication, control, and so on. Third, demanding requirements and complex decisions. So this means to satisfy more diverse use cases, stringent requirements in the future, the role of data and data-driven approaches will be increasingly important. So next, I will illustrate the first aspect of our idea, which is holistic network virtualization. Speaking of virtualization, it's necessary to briefly mention network slicing. So the idea of network slicing is to establish virtual networks or slices over the same physical network, one slice for each service. And the benefit of that is to allow service level customization in 5G. In several of our papers, we have illustrated our resource management strategy for slicing. So basically, we do slicing in two stages. There's a planning stage and there's operation stage. The planning stage has a larger time scale, such as 20 minutes or so. And the operation stage has a small time scale, such as millisecond level. And the planning stage is proactive. So in the planning stage, we reserve resources in the slice. In the operation stage, we allocate the reserved resources to each individual device to support their communication needs in real time. So from the description, it can be seen that network slicing is from the perspective of the network or the perspective of service provision. And what is virtualized is network infrastructure and resources. And network slicing supports service level customization. So we want to ask the question, what can we do in virtualization beyond slicing or beyond 5G? And we think it's beneficial to incorporate the perspective of users or the perspective of service demand and to virtualize users. And doing so would allow us to support user level customization. But how to do user virtualization? Well, we use digital twins. The general concept of digital twin is simple. Basically, two things. First, a digital twin is a digital representation of an entity, so a mobile phone or a vehicle or a sensor and so on. Second, there is real-time synchronization between the entity and its digital twin. In the literature, there are different interpretations of digital twins. Some interpret it as a simulation tool. Some interpret digital twins as virtual humans. Our focus is to use digital twin as user data profiles and data processing functions. So basically, in our idea, user digital twins involves two parts. First, data. Second, functions. So the data involved in a user digital twin can be, for example, connectivity and channel information, user service information, user location, mobility, and so on. And functions involved in a digital twin can be user data collection function, user data traffic prediction function, user motion prediction function, say for mobile augmented reality gaming, and user classification or grouping. In the figure on the right-hand side, I'm showing scenario from one of our recent works. We consider an industrial zone in which multiple sensors are deployed. We establish a digital twin for each sensor, and the data in the digital twin is the sensory data quality. And the function in the digital twin is to establish a dynamic model to characterize the time-varying sensory data quality. So we just mentioned user digital twins, which characterize users and user service demands. A user digital twin is not affiliated to any particular service. One user may use multiple services, and one user digital twin can be affiliated with multiple slices. And user digital twins support user-level customization in beyond 5G. We also introduced network digital twins, which are further virtualization of networks or network slices. And a network digital twin has access to general or service-specific data in user digital twins. An example, network digital twin data involves, say, aggregated service demand, slice resource utilization, quality of service, and so on. And the benefit of introducing network digital twins is to potentially enhance service-based architecture in beyond 5G. So by now, I've introduced slicing, network digital twin, and user digital twin. And we have all the building blocks for our holistic network virtualization. The architecture of the holistic network virtualization is shown on this page. We have a physical network on which several slices are created, and we have user digital twins and network digital twins. Data is collected from the network, processed first for each device locally, and then for each service. And then we have a digital twin model control module, which optimizes the digital twin model so that we can deliver optimal service performance. Of course, due to the limit of time, I cannot elaborate on every detail of our design. If you are interested, please check the survey paper below for details. The second aspect is pervasive network intelligence. So without any doubt, AI will play an increasingly important role in beyond 5G networks. And the role of AI involves two parts. First, AI for networking. Second, networking for AI. AI for networking focuses on leveraging AI methods to manage networks and optimize network performance. And the objective is to automate network management and performance optimization. Networking for AI, on the other hand, focuses on enhancing network support for AI applications, such as autonomous driving or mobile augmented reality gaming. And the objective is to support ubiquitous AI on cloud, edge, and user equipment. There are many potential applications in AI for networking. Here I give two examples. So on the left-hand side, I'm showing the example of AI-assisted network slicing. We could use AI to place network functions. We could use AI to optimize vertical parameters, and we could use AI to orchestrate slice resources. On the right-hand side, I'm showing this potential direction of connected AI for network function orchestration. So currently, AI is really implemented in separation, in isolation for each specific network control function, for example, power control. However, the performance of a service depends on all the network functions. So if we can allow AI modules for different network functions to exchange information and collaborate, then we can potentially optimize the service performance. Similarly, there are many potential directions in networking for AI, and here I also gave two examples. On the left-hand side, I'm showing the customized slicing for AI service provision. So basically, AI applications have unique features such as dependence on data, the need for modal partitioning or compression. Accordingly, when we do slicing to support AI services or AI applications, we should take into account the features of AI, say the data flow for training. And by doing so, we can optimize slicing to support AI services. On the right-hand side, I'm showing an example of a network support for collaborative learning. This is from one of our recent works. So in this scenario, we have a device on which a lightweight DNA or a shallow DNA is deployed. And we have an edge server on which a full-size DNA is deployed. A computing task can be executed completely on the device, or partially on the device and then offloaded to the server or completely on the server. So by considering the communication environment and the server's workload, we can do the task assignment and resource reservation in order to support the collaborative learning. So now that we have introduced holistic network virtualization and pervasive network intelligence, it's important to know that these two are not independent. There is interplay between the two. And the interplay first is through data. So digital twins can provide data to empower AI. And AI can provide processing results such as predictive user location to digital twins. The interplay is also through control. So AI can control the digital twin models, and the digital twin model in turn controls the quality and granularity of the data available to AI. So the interplay above facilitates closed-loop network management. So to better illustrate our proposed idea, I'm presenting a case study next. And this case study is from our paper, Planning Stage Resource Management for Multi-Tier Computing. So the network scenario is given as follows. So we have multiple base stations, and we have 3 tiers of computing servers. So there's a computing server at base station or SBS. There's a computing server at network aggregation point or SNAP, and there's a computing server at core network or SCN. And servers at different tiers have different amount of communication, computing, and storage resources. Usually an upper tier server has more resources. And servers at different tier also have different service coverage. So the server at base station covers 1 cell. The server at the NAP covers multiple cells. And the server at a core network covers all the cells connected to this core network. We consider a computing service, which corresponds to 1 slice. So whatever we do in this work, we focus on managing 1 slice. And users generate computing tasks, which need to be assigned to computing servers in the considered service. And the feature of the considered service is the requirement for context data for processing tasks. And the context data could be background scene in augmented reality gaming. And because of this need for context data, servers will need to store some context data in advance. So we assume the server at the core network can store all the context data, while the servers at NAP or server at base stations, they have limited storage space and they can only store part of the context data. If we look at a base station, different context data chunks have different request ratios or popularity. If we look at different base stations, for the same context data chunk, the popularity of it is different at different base station. And this reflects the location dependency of the service. So given this scenario and the service, we want to do planning stage resource reservation. So conventionally, the resource reservation for planning stage is done as follows. So there's a time interval for planning. And before each interval, a decision on whether to adjust the resource reservation or reconfigure the resource reservation needs to be made. So basically, conventionally, the resource reservation is reconfigured periodically. The reconfiguration is necessary in order to adapt the changes of service demand over time. However, the reconfiguration also incurs cost. So the conventional way of periodical reconfiguration yields low cost effectiveness for the given adaptivity. Basically, we can reconfigure frequently, which means the time interval can be very short. This would guarantee high adaptivity, but the cost is also high. Or we could reconfigure infrequently, which means the time interval will be long, and this means the cost is low. However, the adaptivity is also low. Our approach is to reconfigure the resource reservation only when beneficial or only when needed. And this is to balance cost and gain. So based on the description, you can see that there are two types of decisions that we need to make. First, whether to reconfigure the resource reservation or not before each time interval. Second, if yes, what would be the optimal resource reservation solution to use for the upcoming time interval? So the objective is to minimize the weighted network resource usage and the reconfiguration cost over k time intervals in the future. There are some challenges to solving this problem. First, spatiotemporal variations. The aggregated computing task loads and the aggregated context data request ratio change over time and over space. So on the right-hand side, I have an illustration figure. So you can see that the service demand in one time interval looks very different from the service demand in the next time interval. Second, sequential and coupled decision making. There's coupling between resource reservation and task assignment. There's coupling among computing, communication, and storage resource reservation. And the reconfiguration decision has an impact on potentially many subsequent intervals. Third, lack of prior information. Since we're doing proactive resource reservation, we don't have the information on exact user locations, computing loads, or context data at the time of decision making. To solve this problem, we first introduced our digital twin model. As mentioned before, our digital twin includes data and functions. So in this work, the UDT data characterizes user service demand. So specifically, the data included in the digital twin of a user includes the number of computing tasks and context data requests generated by the user in the coverage of each base station in each of the past t intervals. And the functions involved in a digital twin includes analyzing historical service demands and predicting service demand in the next interval. And based on our digital twin, we can group users both based on their mobility pattern, or more specifically, the sojourn time under the base stations. And the purpose of grouping the users is to make more fine-grained planning. Since our work involves reserving resources and assigning computing tasks, so we need to establish some models here. Instead of going into details of the model, I'll just stay on the high level and briefly explain some constraints. So basically, each server has limited computing resource, and we also limit the computing time for all tasks offloaded to any server at any time interval. And the overall computing cost is determined by the task load and the task assignment, and can be expressed using this formula. We also have a storage model. Similarly, each server has a limited storage resource, except for the server at the core network. The overall core storage cost at a server is determined by the reserved storage space. Each server stores the locally most popular data chunks based on the data from user digital twins. If a server doesn't have the required context data in order to process an assigned task, then the server will need to download the context data from an upper tier server. The communication model involves two parts. The first part is for context data downloading. As mentioned previously, if a server doesn't have the required context data, it will need to download it from an upper tier server, and this incurs communication cost. And this communication cost is determined by the computing task assignment and the storage resource reservation. The second part of the communication model is for task offloading. So each user needs to offload its generated computing task to a base station, which may need to upload the task to an upper tier server, depending on the task assignment. And this incurs communication cost. And the communication cost in this part is determined by the computing task assignment. So overall, the resource usage cost for one interval can be expressed using the following formula. And in this expression, the decision variable R here includes task assignment, the storage resource reservation, and the computing resource reservation. In addition to the resource usage cost, we also need to know the reconfiguration cost. And we can use a binary indicator to denote whether we reconfigure the resource reservation for an upcoming interval or not. The cost for reconfiguration will be a constant in our model. And because of that, our resource reservation evolves over time using the following expression. So basically, if we do not reconfigure the resource reservation, then the resource reservation in the upcoming interval is the same as the resource reservation in the current interval. If we do reconfigure the resource reservation, then we need to derive a new resource reservation, optimal resource reservation, based on the computing task load and the context data request ratio. So the overall problem is formulated as follows. So we want to minimize the weighted sum of resource usage and the reconfiguration cost per task over k time intervals. And we have computing resource constraints, storage resource constraints, communication resource constraints, and we also have a constraint that says all tasks should be assigned somewhere. And among the constraints, we have some group-based reservation related constraints. So to solve this problem, we use the following overall approach. So basically, we divide the problem into two parts. The first part is for resource reservation, and the second part is for resource reservation reconfiguration. So for the resource reservation part, we use analytical plus historical methods to solve it. More specifically, we use matching theory plus particle swarm optimization. For the reconfiguration part, we use learning-based method. The figure on the right-hand side shows how our user digital twins interact with the solution algorithms in this problem. So for computing task assignment, to solve this, to find the optimal computing task assignment, we need to know the storage resource reservation and spatial task distribution. And this problem is actually a many-to-one matching problem. And to solve this matching problem, we can first transform it to a one-to-one matching problem. And then we can solve a knapsack problem to handle some grouping-based constraints. For resource reservation part, the computing resource reservation is completely determined by the computing task assignment. So once we have the computing task assignment, the computing resource reservation is also obtained. The storage resource reservation is a bit more complex. So we use a particle swarm optimization method to solve it. So we have two loops in this workflow. In the inner loop, this highlighted step represents task assignment, and the outer loop, when converged, gives storage and computing resource reservation decisions. For the reconfiguration decision, since it is a sequential decision-making problem, we use deep reinforcement learning to solve it. The challenge, however, is this problem has a high-dimensional state space. So basically, the state space is the historical service demand, which includes the task loads and context data request ratios at all base stations over t time intervals. To solve this issue of high-dimensional state space, our design of the AI part includes two components, the deep reinforcement part and the meta-learning part. The role of the meta-learning part is to determine whether the service demand in the upcoming interval is similar to the service demand in the current interval or not. If they're similar, then there's no need to reconfigure the resource reservation. But the tricky thing is, how do we define the similarity? So basically, we define similarity based on comparing reconfiguration cost and performance gain. If the reconfiguration cost exceed the performance gain, then we consider, okay, the service demand in the upcoming interval is similar to the service demand in the current interval, and there's no need to reconfigure the resource reservation. The meta-learning part is implemented using Siamese neural network, and this neural network needs to be trained. And when this neural network is trained, we use the output from the second last layer of the latent factor as an input to the DRL part, deep reinforcement learning part. The deep reinforcement learning part is implemented using deep Q networks, and the state of the deep Q network is the latent factor from the Siamese neural network. And the action is whether to reconfigure the resource reservation or not. So binary action. The reward is the negative of the objective function value, since our objective function represents a loss. So basically, the meta-learning part extracts impact of change of service demand on reconfiguration decision, while the deep reinforcement learning part makes the reconfiguration decision. So the benefit of our two-part design is twofold. First, this design increases the adaptivity given the cost. Second, this design reduces the dimension of the problem. So without the meta-learning part, the state space has a dimension shown here. And with our meta-learning part, the state space is reduced to the dimension of 1 times n, while n is the size of the latent factor vector. So to illustrate the performance of our approach, I will introduce some simulation examples. The first example is about resource reservation. So we have 1 server at core network, 2 servers at NAPs, and 6 servers at base stations. We have 600 users, and we compare the proposed algorithm with benchmarks. The proposed algorithm is called RR, resource reservation, and as mentioned before, it includes matching and particle swarm optimization. And the benchmarks are equal assignment, brute force, base station first, and NAP first, each of which combined with particle swarm optimization. So from the figure, we can see that the proposed method actually achieves a performance similar to that of brute force, and both of which has low resource usage per task. The second simulation example is about resource reservation reconfiguration. So the figure on the left-hand side shows the convergence performance when we have a new state. So we compare the proposed method, which includes meta-learning and deep Q network, with a benchmark that only uses the deep Q network. So we can see that when the benchmark and the proposed methods are both trained, and suddenly we have a new state, it takes much shorter time for the proposed method to converge. On the right-hand side, we compare the resource usage and cost versus the number of base stations. And we compare our proposed method with DeepQ network and DDPG. And from the result, we can see that our method achieves much lower resource usage and cost per task compared to benchmarks. So in conclusion, I talked about the motivation of Beyond 5G, introduced some emerging applications, and summarized some potential trends for Beyond 5G. And for holistic network virtualization, I mentioned the integration of networks virtualization and user virtualization. And holistic network virtualization allows us to characterize both service provisioning and service demand. For pervasive network intelligence, introduced networking for AI and AI for networking, and emphasized the interplay between AI and virtualization. And using the case study, I demonstrated a potential way to explore AI and digital twin in automating planning stage network resource reservation. So here are some references used for this talk. Thank you very much for your attention.
Thank you, Dr. Chiga. I think it's a very interesting topic, and 1 hour cannot be enough or even 40 minutes, because each of these elements that you have shared, they have, I mean, we can spend hours on each of them. But thank you so much. We have our attendees, so maybe we can start with our attendees if they have any questions. And then I have a couple of questions that we can go through. So anyone, if what I will do is, please raise your hand if you have any questions, then I will unmute you. Or you can try to unmute yourself if you have any questions. Okay, meanwhile, while we are, let's say, yeah, so Moshuli, you are unmuted.
Unmuted, yeah. So can you hear me?
Yes.
Yeah,
Yeah,
if
great.
you could speak a little louder, please.
Okay. So thank you, Professor Gao, for your insightful talk. So I have a question about how the virtualization can serve the network for AI. So could you tell more about how they considered virtualization technique to support the network for AI cases?
Sure. Thank you for the question. So let me go back to the first one page. I think I can I can use this page to illustrate. So basically, to support AI, we need from networking perspective, we need two things. First, we need high quality and a large amount of data. Right? Second, we need network to provide sufficient capability, say the capability to uploading data and capability to process data. Virtualization, especially on the user level virtualization, allows us to better abstract users and therefore characterize users and collect high quality data from the physical user device. And this data can be provided to AI to empower AI. Second, both user level geotrain and network level geotrain can allow us to enhance the capability of networks to provide, say, bandwidth, computing capability to support AI applications. So from these two aspects, I think we can use virtualization to support AI.
Okay, I see. Thank you very much.
Thank you for the question.
Thank you. So we have another question. Let me just unmute. Yes, please go ahead. Tongkao, we do not hear you. Maybe you can write your question instead in the chat. I think that would be easier. So I have one question. I mean, most of these advancements or additions that we are proposing and we see in many research today, talking about the beyond 5G. So, I mean, we look at what we have in 5G today and the amount of deployment. It's not much. I mean, it's very limited deployment in terms of 5G. If you go a little bit outside the main cities, or if you're not in a country like US, Canada, or somewhere in Europe, I mean, even 5G is not fully deployed. So one of the things that I was thinking that whether the networks, the existing network, can utilize some of these features on the current state of the network. So let's say we have 5G, but we make the networks a little bit smarter, or we update the network instead of just updating everything on the radio side, on the user end, but the network can do some upgrades and provide some better functionality to the user. Maybe that is first step before we say that everything can be updated. I'm just talking about in terms of coverage and cost perspective. So have you thought of any of these things or studied in any of your research?
Thank you. Thank you for the question. So basically, you're saying whether it's possible to apply some extension or some small adjustments in existing networks instead of revolutionize the entire network to support emerging applications, right?
Yeah, that's right.
Yeah, so that's a great question. And I think the answer is yes and no. So from my personal opinion, so there are things that current network architecture, current network design would allow us to do. For example, 5G introduced network data analysis, right? And this potentially provides interface for AI. And 5G, or at least 5.5G, is introducing more elements related to AI, as I mentioned before. So in terms of integrating some AI component for network management, so this should be possible, in my personal opinion. However, what we are proposing involves a level of granularity that is beyond 5G. For example, when we talk about user service user level customization, 5G doesn't support that. And currently, 3GPP specification, at least I haven't seen anything that would allow us to do something like that. Meanwhile, in the future, user-centric networking will become important. Again, that's my personal opinion. So things like that, we may not be able to achieve by adjusting existing network architecture or network design. So that's that's my answer to the question.
No, that perfectly makes sense, because I mean we are always limited by what we have and what can be done on the existing network. And also, I mean, in terms of architecture, we do not have so much flexibility. So yeah, either we wait to revolutionize or we just live with the limited options that we have. So earlier, Pongao Zhu was trying to ask some question, and we have the question in the chat now. The question is, could we get some insight or vision about the differences between network digital twins and digital twins from the industry, like what NVIDIA is proposing? So what are the differences, if we just say something about?
Okay, so I haven't checked the dual twin that NVIDIA is proposing, but the purpose of our dual twin is to focus on more on the service provision side of the service. For example, we have already slicing, right? And slicing already takes into account the quality of service, the network function, deployment, all those factors. But we want to establish a closed loop between the service demand, the current service performance, the current service management solution, and enable an automated, service performance optimization. So that's our purpose of dual twin, our network dual twin. And our network dual twin, unlike slicing, is not a passive entity. Our network dual twin should be able to evolve over time. And that's why I keep emphasizing automating the service performance. So our dual twins also evolve over time. The models change over time, and the specific data collected change over time. The functions involved can change depending on the performance of the service. So I guess that's one of the highlights of our network dual twin. Thank you for the question.
Thank you. Yeah, and thank you from the Congo also. So any other questions? Yeah, we have one more raised hand. So let me unmute you. Yeah, please go ahead.
Thank you for your great presentation. Actually, I have a question on this page about dual twin. So, it seems that both user dual twin and network dual twins designed to collect and more precisely process data. But some data, especially about users, that needs to be collected from the application providers. For example, if we have TikTok or we have other AR, VR-based applications, we can only fetch data from those application providers. So how do you think the possibility or feasibility for the collaboration between the application service provider and the telecommunication companies to share the data about the users for achieving this network digital twin in 6G?
Thank you. That's a great question. That is true. What you mentioned about the difficulty of getting some application-specific data, say how often you tap the screen when playing a game, right? So this kind of data can be difficult to collect without support of application, and this is not really a technical challenge anymore. However, I do believe that there are some common user level data, as I mentioned before, say user location, right? So based on 5G positioning and or user traffic pattern, right? So you may not be able to see into the traffic, but you can collect some traffic pattern based on users' data sending behavior. So those data could be available. In like some of them are already available, right? So I would think in the future we would have more types of user level data available due to the increased capability of networks in terms of sensing, positioning, control, all those. Regarding specific application level data, yeah, that's really difficult to predict. But I hope if there is a strong incentive for networks to support certain types of application, then there's a chance for the applications to agree to share such data.
Okay, thank you for your answers.
Thank you for the question.
Thank you so much. Any other questions? If not, we can wrap up the call. And once again, I would like to request if anyone is interested to learn more about the VTS Ambassadors Program, if you have any recommendations of your colleagues or friends, please go ahead. We need a few more for this year. So I will be happy to explain what it is and what is needed. And I would like to thank Dr. Gao. Really appreciate the time, and we will be happy to hear more from you. I mean, it was exciting, and I will be happy to invite you again, and if you have some new results to share with us.
Thank you very much, Dr. Abbas, for hosting and for arranging this event, and thank you to everyone for joining the talk.
Yeah, have a good day and happy Easter to all.
Thank you and have a great day. Bye.